Hello, my name is Bo James. Welcome to my research to practice narrative for the final product I created, assignment 3 in EDUC 5404G. This presentation shall function as a companion guide to connect the final product I developed in this course to recent supporting literature. A condensed version of this presentation was provided to peers for review during our final class of the semester. The final product that I developed for assignment 3 is a course outline for a new course in post-secondary automation with accompanying support documents. As an overview, I will provide an introduction to the post-secondary discipline that I teach. I will continue to provide background on the specific topic of my course outline and discuss the connection between the outline and an industrial need to educate technical personnel for employment. An explanation of how research has informed both the learning environment and course learning outcomes of the course rounds out this presentation. I primarily teach in a discipline known as Electromechanical Engineering Technology, or EMTY for short. EMTY is an advanced college diploma program that specializes in the electronics programming and mechanical technologies used in industrial automation, instrumentation, and robotics control applications, as shown in the photos on this slide, directly from our laboratory. In their graduating semester at Durham College, EMTY students are enrolled in a capstone course titled Supervisory Control and Data Acquisition. According to Bentley Systems, a SCADA system is a computer-based interface that permits operators to remotely monitor and control field-mounted equipment from a centralized location. SCADA systems are prevalent in building automation, manufacturing, oil and gas, power generation, and water treatment industries, to name a few. The first course learning outcome included in the SCADA outline requires students to identify the fundamentals of a SCADA system before beginning to develop one using an industrial software package. This infographic illustrates the purpose of a SCADA software development environment when applied to a water treatment application. At the top of the infographic, we find the main pump station computer that allows plant operators to connect to multiple remote pumping stations distributed throughout a city to control automated equipment, monitor reservoir levels, and acknowledge alarms from a central computer using graphic screens similar to the one shown in this slide. The final products developed for this assignment include a SCADA course outline, a sample lecture lesson plan, and a summary of laboratory activities table that maps learning activities in the lab to empirical research and the course learning outcomes. Research studies were examined to assist in the selection of the course learning outcomes and provide frameworks for the design of the laboratory learning environment of this post-secondary SCADA course. Driving the development of this course in post-secondary education, Senka, Stoic, Jovanovic, Tarjan, and Stankovsky posit there is a need for engineers with knowledge and skills in various areas, including mechanics, machine design, programming, electronics, embedded systems, control, and automation. From a learning environment perspective, this SCADA course will be facilitated face-to-face through 2 hours of laboratory work and 2 lecture hours per week for a 14-week semester. Lecture activities will be designed to support students in their laboratory design work. For example, the sample lesson plan included begins with a connection activity that illustrates the benefits of upgrading an older water treatment system to a new SCADA software system in Kingston, Ontario. An introduction to the fundamentals continues to prepare students for the review of a case study in groups to answer guiding questions that relate to the purpose of implementing a SCADA system in an industrial water treatment project. According to Bazadin and Kamat, education in science and computer technology programs need to facilitate activities that connect in-class concepts to real-world applications. Furthermore, Noel's principle of andragogy cites the importance of providing clear instructions, activity motivation, and temporary guidance for adult learners. D'Souza and Rodriguez note that although engineering graduates may have mastered a series of technical learning outcomes, there appears to be a shortfall in graduates' collaborative working skills as they enter the employment field. To address this skills gap, essential employability outcomes 7 and 8, known as soft skills, have been embedded into the SCADA course outline as shown in the table. Recent research from a promising collaborative working model from industry, titled Agile Principles, provide a useful framework upon which to employ these outcomes. When applied to technical education, D'Souza and Rodriguez term these principles as extreme pedagogy. which is founded on the pillars of student participation, goal-oriented instruction, pair-based learning, and frequent assessment. From a practical perspective, these founding principles have informed the design of a collaborative laboratory working environment as described further on the next slide. Firstly, programming exercises planned for this course are project-based and learner-centric, requiring students to apply skills yearned from tutorial exercises and lecture guidance to project designs carried out in the lab. Stemming from Zapater, Malagon, de Goyeneche, and Moya's guidance, group programming exercises will be assigned in pairs to optimize learning potential and avoid situations that can result in a few keen students carrying the workload for others. Further to this, formative verbal feedback will be provided to students on a weekly basis to help prepare them for their formal lab demonstrations that typically occur every 2 weeks. As described by Ronan, formative assessments aim to provide students with an indication of how they are proceeding through a learning goal. Shifting our focus from the learning environment to research that has informed content in the SCADA course, the course learning outcomes from the outline are presented here. As an overview, students begin the course by identifying components of a SCADA system before moving on to develop a SCADA system of their own. CLLs 2 and 3 relate to the programming of graphic interface screens and real-world automation computers, as shown in these photos, to control and monitor a pumping system in the lab. CLLs 4 through 8 focus on specific aspects of a SCADA system that students need to include in their projects through hands-on practice activities in the lab. Adamo, Adavissimo, Cavone, and Giaquinto highlight in their seminal article the importance of designing laboratory exercises that allow students to develop applications using a real-world approach. The authors continue in their study to describe that the core of an EMTY program shall relate to programmable logic controllers and SCADA systems, technologies that these CLOs exude. Next, I present the Summary of Laboratories Activity Table. A portion of this table has been shown to illustrate planned laboratory activities for each week of the semester. The content activity is mapped to the specific course learning outcomes, or CLOs, discussed previously. In the final column, reference to research findings that support the inclusion of each laboratory topic is cited. Exercises 1 through 4 include tutorial and programming activities that introduce students to the use of emulators for programming practice before moving on to real-world live controllers. In a seminal SCADA course design study, Adamo, Adavissimo, Cavone, and Giaquinto suggest the use of emulators as a cost-effective replacement to real-world controllers. In another study, Sahin, Olmaz, and Isler had to utilize smaller-scale microcontrollers for students to program, as the real-world controllers were cost-prohibitive. For the SCADA course I am designing, emulators will be introduced as a means of practice only, and the use of scaled-down microcontrollers will not be considered. Students will develop and ultimately test their interface screens and programming code using industrial-grade software and hardware found in our established laboratory. Continuing with our look at the course learning outcomes and how they relate to lab activities, authors emphasize that with today's technology, it is possible to use a common personal computer in order to implement even complex remote supervisory tasks of simple as well as highly sophisticated industrial plants. In this assertion, the authors highlight the ability to create SCADA operator screens to control and monitor equipment from remote locations. Laboratory activity number 5 is a tutorial exercise positioned to guide students through the development and testing of a remote version of their graphic screens. These are known as client applications, and they will be installed on computers located in different locations than the equipment that it physically monitors. Furthermore, from within the client application, students will configure user accounts that permit various access levels depending on the job title an employee maintains. For example, an instrumentation technologist will be able to manipulate and control all parts of the SCADA system from a remote location. Yet a business manager will primarily have access to monitor the system and print logged data reports, like the sample shown here. Satencevez and Bayender underscore the importance of building SCADA applications with levels of password protection in order to prevent unauthorized users from accessing secure system data. As the second half of the SCADA acronym suggests, developing learners' abilities to acquire data from field instruments is paramount. Once data has been acquired by system designers, there is a need to store it electronically for current and future auditory purposes. Lab activity number 6 will guide students through the configuration of data logging parameters in the SCADA software package. For example, data from a pressure transducer or a sensor in a monitoring tank found in the laboratory can be logged in order to generate graphing reports using common computer software as shown in this screenshot. Finally, Tutorial and Programming Design Labs 7 and 8 introduce students to two emerging attributes found in new SCADA systems: the application of wireless technologies for system communication and the reporting of system alarms and acknowledgements. Recent advancements and flexibility benefits of wireless communications are making their way into new automation systems, which include alarm monitoring and acknowledgement. Having access to industrial systems using smart device internet technology brings about concerns from a cybersecurity perspective. Albert in 2014 cited the importance of improving the awareness, knowledge base, and programming skill set of system designers through post-secondary education in order to protect industrial SCADA systems against potential cybersecurity threats. As such, students will be introduced to a software package known as Win 911 that permits the secure configuration of alarm notification and acknowledgement tracking for internet-connected smart devices. Education that affords learners the ability to monitor system faults from a remote device permits convenient troubleshooting of system issues from up to thousands of kilometers away. In reported findings from a study related to the development of SCADA labs for post-secondary education, the absence of troubleshooting and fault-finding exercises were noted as key attributes that should be included in future course designs. In this presentation, I provided an overview of how research has informed curriculum decisions made in the development of a SCADA course outline. Frameworks from research studies have also contributed to the design of a project-based laboratory learning environment for third-year EMTY students. Founded on recent literature in the automation domain, the final products developed for this assignment can be applied to other SCADA courses in EMTY post-secondary education across Ontario. Thank you for viewing. My reference list is provided here.